The video introduces the winLIFE viewer and its basic functions. 3 models are shown, which differ in many respects. The first model is a welded structure consisting of shell elements. The second model is constructed from solid elements and is not welded. The third model consists of solid elements and has several weld seams. A notable feature here is the bolt tension resulting from a pre-assembly process. We open example 22 from the winLIFE help section and take a closer look at the interface to the viewer. The method is set to welded. The FE interface specifies the import of finite element results. In addition to the simple stress files, known as LST files, results from NAST-RAN, ANSYS, Abacus and other programs can be imported into winLIFE. This video focuses primarily on the viewer. Therefore, settings in winLIFE that do not relate to the viewer will be omitted. The interface with NAST-RAN is used at the frame corner. The mesh data, that is, the FEA geometry file, is imported, along with the OP2 file containing the stresses. The applied force in the FEA calculation is entered. There are several methods for weld seam calculation. We select linear extrapolation, which corresponds to the structural stress concept with 2 support points. We set the distances of the support points from the weld seam to 0.4 and 1.0 times the sheet thickness. We define the weld seams in the viewer. Here, the comparative stresses according to von Mises are shown on the model. If the results are hidden, the various plates become more clearly visible. The viewer performs a search for weld seams by identifying the connections between different plates. These nodes are then placed into sets. Several weld seam lines or weld joints have therefore been found. An additional weld seam can be created by manually generating a node set. We will demonstrate this in the second example model. In the fatigue life calculation, so-called attributes can be taken into account if required. Attributes are properties such as temperature or surface roughness. These attributes can be assigned to specific sections of the model. Here we show how to use the sheet thickness attribute in the fatigue calculation. The sheet thicknesses can be specified manually or, as shown here, determined automatically from the FE model. To ensure the attributes are used in the winLIFE calculation, a tick must be placed. Similarly, the node sets marked with a tick are calculated. The model is now ready for calculation. Further winLIFE settings will not be shown here, as the focus of this video is on the viewer. Let's take a look at the results. The other 2 models in this video demonstrate further functions of the viewer. The second model demonstrates the integration with ANSYS. The winLIFE project is titled Example 19 RST. Here ANSYS CDB and RST files are used. We start by specifying the geometry file. The FE result file was selected automatically because the file names are the same. The FE calculation in ANSYS was performed using 1 Nm. We therefore leave the value 1 in the FE force column. The volume model selected here is well suited to demonstrating the influence of the stress gradient. We can see the model in the viewer with the comparative stresses. The model is being bent. The highest stresses are found in the circumferential notch. We switch the display to stress gradient. The node number and the corresponding output value can be displayed in a text field. Only 3 nodes should be selected for the calculation in order to reduce the calculation time. To do this, a node set is created. A name for the node set can be specified if desired. 3 nodes from the notch base are selected. There are other selection methods available for selecting nodes, such as a selection box. We can now see the node set that has been created. The attributes are available. However, they are slightly different from those of the welded components. The new node set is marked with a tick and is therefore used in the fatigue life calculation. We can now see the damage sum for the 3 nodes. The exact values of the nodes can be displayed. Further output values are available. The stress gradient is included in the results report. This is approximately 1.071 at this node. This results in the support factor and consequently the increase in fatigue strength. The third model is a welded structure from the automotive industry. The aim here is to demonstrate the interface with PMAs. In this calculation, 2 load cases are to act simultaneously. Once again, the geometry file and the FE results file are specified. The load cases are selected from the PMAs post file. We are again using the structural stress concept for the weld seam calculation. We zoom in on the section of the model to be analyzed. In the node sets, we can see the existing weld lines 1 and 2. These welds have already been created manually to keep the example from becoming too complex. The weld lines are easier to see when the results are hidden. This model is well suited for demonstrating the section plane function. The model is sectioned in the X, Y, and Z directions. The internal model structure becomes visible. Hiding elements is also demonstrated. We see the attributes again. In the first model, we looked at the attributes and defined the sheet thickness. We will now perform the calculation for the 2 welds. The calculation time is shown in accelerated form in this video. The total damage result is displayed automatically. The viewer opens. We can see the 2 welds with their damage values. The highest damage values occur on the rear side of the model. Many functions are available in the viewer for a more detailed analysis of the model and the results. To keep this video from becoming too long, please refer to the winLIFE help section. The weld seam coordinate system displayed here indicates the direction of the stress extrapolation.